All right, so we have started a new section 2.1, defining functions. You have been composing code that calls Python functions since the beginning of this book site. In this section, you will learn how to define and call your own functions. Functions support a key concept that will pervade your approach to programming from this point forward. Whenever you can clearly separate tasks with a computation, you should do so using and defining functions. The effect of calling a Python function is easy to understand. For example, when you place a math.square root (M-S-B) in a program, the effect is as if you had replaced that code with a return value that is produced by Python's math.square root function and pass the expression a-b as an argument. If you think about what the system has to do to create this effect, you will see that it involves changing a program's control flow. You can define a function using a def statement that specifies the function signature, followed by a sequence of statements that constitute a function. For example, harmonic CF defines a function harmonic that takes an argument n and computes the nth harmonic, as described in section 1.3. It also illustrates the typical structure of a Python program having three components: a sequence of import statements, a sequence of function definitions, and an arbitrary global code or the body of the program. So a quick look. Simple harmonic. So we have an input, we have some imports, we have a def statement that finds a name. This can be any name, harmonic. I can call it Happy Feet if you want to, or Hello World. This name you can choose. And input, and then has some input, and return is the output. So Python executes the global code when we invoke the programming by typing Python harmonic cf.pf on the command line. That global code calls a harmonic function defined earlier. For the purposes of illustration, we have made the user interaction part of the program a bit more complicated than in section 1.3. Control flow. The diagram shows at the right illustrates the flow of control for Python harmonic cf for 2 and 3. Harmonic cf.py 1, 2, and 3. First, Python processes the imports statements, thus making all the features defined in assist and standard I/O modules available on the program. Let me just go into a bit more detail here with my pointer. So again, we first do the imports, right? First do the imports. Next, Python processes the definition of harmonic function at all lines 3, 4, and 8, but does not execute the function. It's very important. It actually skips this piece of code, right? For example, it does this. It skips, it processes it, but doesn't do anything with it yet. Very important. Doesn't do anything yet. It doesn't do anything with it yet. Python executes a function only when it is called. So it is not called yet. By calling it, we have to define it in this way. So this is just this is how we are creating the function, but it's not being used yet. You can only use it by calling it by its name and give it some input value. So Python first executes a statement in the global code. Here's a global code. The for loop is the global code with the for statement, which proceeds normally until Python begins to execute the statement value equals harmonic arg. So once it sees this, it bounces back. It moves back to this code. It goes back to this code in the beginning and runs it, starting by evaluating the expression harmonic when arg is 1. To do so, it transfers control to the harmonic function. The flow control passes the code in the function definition. Python initializes the parameter variable into 1 and local variable to 0.0, and it executes the for loop with harmonic, which terminates after one iteration with total equal to 1. So go back here again. So it does this, and then the code jumps to this function and completes this local code to this code block over here. Does this, and then completes that, prints out the value, repeats a for loop, and the for loop gets an argument, goes back to this function, and then repeats the loop. So this is the arrows that it's trying to draw out. And Python executes a return statement at the end of the definition harmonic, causing flow of control to jump back to the calling statement value equals harmonic arg, continuing from where it left off, but now with expression harmonic arg replaced by 1. Thus, Python assigns 1 to value to 1.0 to value and writes it to the standard output. Then Python iterates the loop once more and calls harmonic function second time with n initialized to 2, which results in 1.5 being written. The process is then repeated a third time with arg, then n equal to 4, which results in 2.033 being written. Finally, the loop terminates and the whole loop process is complete. As the diagram indicates, the simple code masks a rather intricate flow of control. So this shows the flow of control, what happens. I is 1, arg is 1, harmonic, get the results, and then repeats the step. Harmonic 2, harmonic 3, harmonic 4. A formal function call return trace. One simple approach is to follow the control flow through function calls is to imagine that each function writes its name, an argument when it's called, and its return value before returning, with indentation added on calls, and the result enhances the process of tracing a program by writing values of its variables, which we have seen using since section 1.2. An informal trace of our example is shown over here to the right. So I can maybe just show this. So, for example, I was 1, and then arg was 1, and then the harmonic function was passed to that and got the value of 1. Inside harmonic, we had total equals 0.0, and then total became 1.0, and then it returned 1.0 to the for loop, and then the value became 1.0. I iterated, so it became 2, arg became 2, and then harmonic function repeated. Harmonic became 2, and then the process repeats continuously as shown. Basic terminology. So there are several concepts rolled up in the idea of a mathematical function, and there are Python constructs corresponding to each, as summarized in this table. A function, input value, output value, formula, and independent variable. So Python construct, this is a function, the argument, return value, function body, and parameter variable. So the description is this is mapping function. This is the input to function, input of function, function definition, a symbolic placeholder of input value. When we use a symbolic name and a formula that defines a mathematical function, such as fx1 plus x plus x squared, symbol x is a placeholder for some input value that was substituted into the formula to determine output value. In Python, we use a parameter variable as a symbolic placeholder and refer to the particular input value where the function is to be evaluated as an argument. All right, so let's look at the function definition again. Try and zoom in here. The first line of a function is a definition, known as a signature, given a name to the function and to each parameter variable. So we can screw with this, we can say def harmonic. This is the name or the signature of the function. Harmonic. You can call it again whatever you want, but this is a signature. Signature consists of def, function name, harmonic, a sequence of 0 or more parameter variables. Here we have n, separated by commas and enclosed in parentheses. This is the input over here. And then we finish with a colon over here, just like we've done with other code blocks like for loops and while loops and if conditionals. The indented statement follows a signature defined the function body. So if you do enter, you'll see that it indents it because now this is a code block. The total plus equals 1.0 divided by I. Well, that's actually what it's just first total 0.0, and then you have for I in range of 1 plus 1. Another code block actually we're working with. And then you have a return. What you're returning. returning a total. So the function body can consist of the kinds of statements that we did in chapter 1. It can also contain a return statement which transfers control back to the point where the function was called and returns the result of the computation or return value. Body may also define local variables, which are variables that are defined only inside the function in which they are defined. So total is only defined locally and only used locally. Function calls. As we have seen throughout a Python function call is nothing more than a function name followed by its arguments, separated by commas and enclosed in parentheses. Each argument can be an expression, which is evaluated and the resulting value passed as input to the function. When the function finishes, the return value takes the place of the function call as if it were the value of a variable caps within an expression. Multiple arguments. Like a math function, a Python function can have more than one parameter variable, so it can be called with more than one argument. For example, then have multiple input variables A, B, C if I really want to. Multiple functions. You can define as many functions as you want in a Python file. The function are independent except that they may refer to each other as among calls. So you have as many functions as you want. You can even have harmonic 1, harmonic 2 Python file. However, the definition of a function must appear before a global call, right? So I cannot call it here. I cannot call it here like 1, 2, 3, 4. It must happen. It cannot happen before the function is defined. It must happen afterwards. What's happening here? There's a reason that the typical Python program consists of imports, function definitions, and then the arbitrary global code in that order. Multiple return statements. You can put return statements in a function wherever you need them. Control goes back to the calling program as soon as the first statement is reached. Single return value. A Python function provides only one return value to the caller, or more precisely, it returns a reference to an object. This policy is not restrictive as it might seem because Python data types can contain more information. So you can return a list, for example. For example, you will see later in the section that you can use arrays as return values. Lists or arrays, right? Scope. So the scope of a variable is that a set of statements that can refer to a variable directly. The scope of a function local parameter variable is limited to the function. The scope of a variable defined is a global code known as a global variable is limited to the Python file. So for example, I'd have a value called say like, value equals 5. So let me get rid of these multiple ones. So this variable, this variable defined is can only be used within the function. You cannot say print value because it is not defined in a global code. And you can clearly see something is not global, but it's indented, right? It has the spaces in the beginning. It's only inside this function. So this will give an error if you run it. A global code x is equal to 5. X, no indent at the beginning, it means it's a global variable, it can be used everywhere in the code. Therefore, global code cannot refer to either functions, local or parameter variables, nor can one function refer to either local or parameter variables that are defined in another function. So if you have another function, for example, like this one over here, so over here, if we just kind of check what. So nor can one function refer to another one. So if I have like value 6, for example, here, value 5, they are unique to this code, right? They are unique to these functions. When a function defines local or parameter variable with the same name as a global variable such as I and harmonic, the variable name in the function refers to local parameter, not the global one. So they might have the same name, but they are unique to these functions. While the code in a function can refer to a global variable, it should not do so. All communication from a caller to a function should take place via the function's parameter variables. All communication from a function to its caller should take place via the function's return value. Default arguments. Python function may designate an argument to be optional by specifying default value for the argument. For example, I'm just remove these. I can say n equals 1. So if I want to call it, remove this again, and say harmonic. If I don't, I can call the function like this and it will return a value. And then it will use n equals 1 as a default. Or if I can say n equals 5, it will override n equals 1 and replace it with 5. So we've already encountered a few examples of this feature. You can specify an optional argument with default value in a user-defined function by putting equal sign followed by a default value, as I've shown, after the parameter variable in the function signature. You can specify more than one optional argument in the function signature, but all the optional arguments must follow all of the mandatory arguments. The harmonic function in the table below shows the use of the default argument. Side effects. P function is a function that, given the same arguments, always returns the same value without producing observable side effects, such as consuming input, producing output, or otherwise changing the state of the system. In computer programming, it is also useful to define functions that do produce side effects. In fact, we often define functions whose only purpose is to produce side effects. An explicit return statement is optional. Such a function control returns to the call after Python executes a function's last statement. Functions with no specified return value actually return the special value none, which is usually ignored. The drawing triangle function in the table below shows side effects and does not return a value. Type checking. In math, the definition of a function specifies both the domain and range. For example, for harmonic numbers, the domain is positive integers and the range is positive real numbers. In Python, we do not specify types of the parameter variables or the type of return values. So we're not saying the type is a string, integer, float, bool, or the return is type int bool. We're not specifying that at all. The domain is a positive integers and the range is positive real numbers. In Python, we do not specify types of parameter variables or type of return, as long as Python can apply all of the operations within a function. Python executes the function and returns a value. If Python cannot apply operation to a given object because it is of wrong type, it raises a runtime error to indicate the invalid type. The flexibility is a popular feature of Python known as polymorphism because it allows us to define a single function for use with objects of different types. The table below summarizes our discussion providing examples of functions. So if we have a primality test, checks if a number is prime, gets a value n, outputs true, if it's true or not. We have a hypotenuse, work out hypotenuse, has input is two values a and b, and returns the square root of that, which gives a hypotenuse. Harmonic number works out the harmonic number of the two inputs, n and r equals 1. Here, r is a default. If you don't specify r, it will use 1 as a default. Draw a triangle. Here's a definition to draw a triangle with values drawing the lines. Implementing math functions. We now consider two important functions that play an important role in science, engineering, and finance. A Gaussian distribution function characterized by a familiar bell-shaped curve and defined by this formula. And the cumulative Gaussian distribution function is defined to be the area under the curve, defined by phi above the x-axis and to the left of the vertical line x equals z. Function to calculate these functions are not available in Python's math module, so we develop our own implementations. Closed form. In the simplest situation, we have closed form math formula defining our functions in terms of math functions that are implemented in Python's math module. This is the case. So again, function to calculate pi and big pi are not available in Python math module, so we develop our own implementations. So we did that. So this is the case for a small pi. So a function PDF corresponds to the math definitions, which is easy to implement. For convenience, our Gauss file over here, let's see, check it out, uses the default arguments pi 0 and delta 0 or sigma 0, and actually computes the pi function for you. So pi, PDF, and pi and big pi works as the CDF. So it returns the value of Gaussian probability function with mean 0 and standard deviation. So I have multiple functions that we're creating. So again, this is also explanation of how you can use one file with multiple functions in it. No closed form. If no formula is known, we may need a more complicated algorithm to compute function values. Situation is the case for pi. No closed form expression exists for this function. Taylor's series approximation to the ratio of pi and sum pi turns out to be an effective basis for the function. The formula readily translates to the Python code for the function CDF in Gauss.py. Small, respectively large z, the value is extremely close to 0, respectively 1. So the code directly returns 0, respectively 1. Otherwise, it uses the Taylor series to add terms until sum converges. Again, for convenience, Gauss.py actually computes big pi z using this formula with the defaults 0 and 1. Using function to organize code. With the ability to define functions, we can better organize our programs by defining functions within them when appropriate. For example, Kuban calculator, we've seen before in section 1.4, a better version of it. Given n, compute a random coupon value. Given n, the coupon collection experiment. Get n from the command line, then compute, write the result. Whenever you can clearly separate tasks from the computation, you should do so. So this was the functions, two functions to get the coupon, and this was the implementation of it. So this is code we've done already in 1.4. Passing arguments and returning values. Next, we examine the specifics of Python's mechanisms for passing arguments to and returning values from functions. Call by object reference. You can use parameter variables anywhere in the body of a function in the same way as you use local variables. The difference between a parameter variable and a local variable is that Python initializes the parameter variable with the corresponding argument provided by the calling code. We refer to this approach as call by object reference. One consequence of this approach is that if a parameter variable refers to a mutable object, something that changes, and you change that object's value within a function, then this also changes the object's value in the calling code because it is the same object. Next, we explore the ramification of this approach. Immutability and aliasing. So here's an example where we have I equals 99, j equals I, and let's increment j equals j plus 1. Let's see what I is and what j is. Okay, so print I and print j. So I is 99 and j is 100. See, I did not change to 100 as well. As discussed in 1.4, arrays are mutable data types because we can change array elements. By contrast, a data type is immutable if it is not possible to change a value. It is not possible to change a value of an object of that type. The other data types that we have been using is int, float, string, and bool are immutable. In an immutable data type, operations might seem to change a value actually result in the creation of a new object, as a result in this example I've done shown you before. First, I equals 99, creates integer 99, and assigns I to reference to that integer. J is equal to I, assigns I an object reference to J. So both I and J reference the same object, the integer 99. Two variables that reference the same object are said to be aliases. Next, J plus equals 1 results in J referencing an object with value 100. But it does not do so by changing the value of the existing from 99 to 100. Indeed, since int objects are immutable, no statement can change the value of the existing integer. Instead, that statement creates a new integer 1, adds it to the integer 99, creates another new integer 100, and assigns j to a reference to the integer. But I still references the original 99. Note that the new integer 1 has no reference to it in the end. That's the system's concern, not ours. So integers, floats, booleans, and strings as arguments. Whenever you pass arguments to a function, the arguments and the function's parameter variable become aliases. In practice, this is the predominant use of aliasing in Python. For purpose of illustration, suppose we need a function that increments an integer. Discussion applies to any more complicated functions as well. A programmer new to Python might try this definition. For example, we have def inc j, and j plus equals 1. What do you think the and then to expect to increment an integer I with a call inc I. Code like this would work in some programming languages, but there's no effect in Python, as shown in the figure at right. To increment I, we would use a definition like this. Return J. So this shows what you're trying to do with this function, aliasing with a function call. So a call function with assignment I equals int I. Same holds true for a mutable type. A function cannot change the value of an integer, a float, a boolean, or string. Arrays as arguments. When a function takes an array as an argument, it implements a function that operates on an arbitrary number of objects. For example, the following function computes the mean average of an array of floats. Let's check this. We've seen this before many times. This code, define a function, call it mean, get an input A, have a local variable to this code, 0.0, have a for loop that works out the sum and works out the average by dividing the length of that array and returning it. So this is, for example, 5. Okay, well, that has to be an array. So import standard IO. Well, actually, let's just quickly just do a normal list. 1, 2, 3. Let's see if this works. There we go. So I didn't really enter the standard array. You can try that if you want. I mean, a normal list works just as well. Side effects with arrays. Since arrays are mutable, it is often the case that the purpose of a function that takes an array as argument is to produce side effect, such as changing the order of array elements. A prototypical example of such a function is one that exchanges the elements as 2 given indices in a given array. You can adapt the code that we examined at the beginning of section 1.4. Again, this is the exchange of the code, 2 elements in an array. So now we can adapt this code as follows: exchange. We've done this before with sorting out, sorting out the order or changing or shuffling around. This is very similar to what we've done. We had a temp variable, swapped it around. Formal trace of a call, as shown over here in this diagram, shown on the right. Second prototypical example of a function that takes an array argument and produces side effects is one that randomly shuffles the element in the array, using the version of the algorithm that we examined in section 1.4 again with exchange function as defined. And add it. Yeah, shuffle. Again, define a function shuffle, get an array element, and shuffle it. Again, this is just the same process image. I didn't speak about it yet, but 1.4, when we did shuffling or swapping and ordering, this is the same diagram as we've done before. You can go through it if you want. Arrays as return values. A function can return an array, for example. Consider the following function which returns an array of random floats. So define a random array, A. Define a random A, standard array, create 1D for I in a range of A, return A. So we can create a random array as well. Create a standard array of certain size, use a for loop to do that, return A, which is give a new random variable. Table below concludes our discussion of arrays as functional arguments by highlighting some typical array processing functions. With mean, we can work out the mean, product of 2 vectors of same length, exchange 2 elements in an array, write a 1-dimensional array, and read 2-dimensional arrays of floats. So these are very useful to practice and to work out. So pause the video, try them out, code it, and see the results that you get. But it's good practice in any case. So superposition of sound waves. Notes like concept A have a pure sound that is not very musical because the sounds that you are accustomed to hearing have many other components. Most musical instruments produce harmonics, the same note in other octaves, and not as loud, or you might play chords, multiple notes at the same time. To combine multiple sounds, we use superposition. Simply add the waves together and rescale to make sure that all values stay between -1 and 1. The program, similar to 1.5, encapsulates the sound wave calculation as harmonics. try running this. Again, we're not running sound waves. It won't work in Jupyter Lab. But you can try the code yourself. How you literally adding two arrays to each other, and playing it in the end. Yeah, so that's the end of this session. Hopefully, you learned something about functions and intricacies of it. Yeah, until next time, thank you very much. If you have any questions, again, if you want me to go through more details about the Q&A or exercises, let me know in the comments. Thank you.